All right, shall we get rolling? I still don't really know how best to proceed with today. So last class, as you remember, we really didn't do much new. It was more of just an opportunity for you to work through a harder example of approximating a boundary value problem. And this boundary value problem had two boundary layers. We split up into breakout rooms and people made progress on it. I asked at the end of class for people to kind of vote to see if we should continue breakout rooms or not. And the vote was kind of split. And so does anyone have a strong opinion one way or the other today? So I was kind of leaning towards me going through it, but I wanted to show you all one more thing that pops up with perturbation problems. And in a way, today will be the last kind of lecture on this topic. Thursday, you'll all present your homework. So hopefully you're working on that. And next Tuesday is going to be no class, it's election day, canceling class. And so the following, a week from Thursday, we'll start a new topic, moving on from perturbation methods. I will also probably at that time hand out your midterm. Maybe sometime in the next week, I think I'll hand out the midterm. Maybe even sooner, actually, maybe more like today, because you'll have all the tools you need to do it now.
I'm sorry, so the midterm is a take home?
Oh, hold on. Why can't I hear anything? Say that again, sorry.
Sorry, just for clarification, yes, the midterm is a take home?
Yes. Yep. It's basically sort of like some sort of hybrid between one really long problem or like a project, if you will. Like it's a problem that encompasses non-dimensional linear equations, finding epsilon, then doing a perturbation, then it'll have a boundary layer, so then kind of connecting all this. So it'll in a way be a way for us to connect some of the topics we've covered. It'll be a take home. Yeah, and so I'll get that to you soon. Probably today. And I'll give you ample time to work on it. I was leaning towards just kind of going through the solution of the multi-boundary layer problem, so that I could show you this one other problem that we won't really have time to kind of work through completely, but I would like to just kind of, boundary layers are kind of like one thing that crops up as demonstrating when an approximation is not kind of uniform with the whole domain, and there's kind of one other kind of canonical example of that. So unless anyone strongly opposes, I think I will try to just blaze through what we were doing last class in the breakout rooms, and then introduce you to this other topic that is just something that I want you to be aware of. Okay, so allow me to share my screen. Only the host, oh yes. Along the way, I would encourage you to jump in with questions. Kind of now is the time for making sure that any ambiguities or uncertainties you have in how to solve these problems, we address them. And so, let's see here. Okay. Here's the problem from last class, and you know a lot more about this problem now, and so I can be less coy in the title here. This is not more on boundary layers. This is a problem in which there are multiple boundary layers occurring in the system. And hopefully you were able to use something like ND-solve in Mathematica with an appropriately choiced magnitude of epsilon. Some of you noticed that if you took epsilon too small, then Mathematica kind of gave you some warnings. It doesn't really mean, it's not something I want you to worry too much about right now. As I've said to some of you in breakout rooms, I'd like to repeat to everyone, epsilon is typically something you know in the problem. It is a value that you kind of know going in, or you kind of know in advance, or you know the range, or you know kind of where it might be relevant. And there are things you can do under the hood in Mathematica or any program that is kind of used for solving differential equations numerically. You can kind of play with a variety of settings to get better resolution. So the fact that this might not work as well for very, very small values of epsilon can be overcome, but we're not going to worry about that too long. Okay, so let's just think about this conceptually first. So I'm plotting here y and x, and we know that from the boundary conditions at x is equal to 1, y should equal 1, and at x is equal to 0, y should equal 2. And if you solve this numerically, what you found was that the solution dropped rapidly from 2, and then rose and then dropped rapidly again, and looks something like that. And what you all started working through was kind of recognizing that this is an example in which there's one boundary condition at x is equal to 0. And so there's one boundary layer over here. And the presence of this second boundary condition at 1 and the form of this differential equation led to a second boundary condition, second boundary layer. Let me try to redraw that line. There we go. That's a little closer. Imagine that peak and that orange thing line up nicely. And so what we really have in our constructing of our approximation is an outer solution that lives in here, where we take the outer solution to mean away from the boundaries, essentially, or away from the boundary layers. And we have two inner solutions. We have an inner solution here and an inner solution here. Let's see. I think all of you pretty quickly got through the outer solution. It's, I hate to use this word, but it's as close to trivial as can possibly come about in these types of problems, because what you would first do is look at what's happening as you take epsilon to 0. And so for the outer solution, taking epsilon to 0 completely removes any differential operators from this boundary value problem. So it becomes negative y equals negative e to the x, right? Because take this thing here. So looking at the outer solution allows us to take epsilon to 0, so this term goes away, this goes away, and what we're left with is this, which is no longer a differential equation. You can't apply any boundary conditions, and you have a solution that says that y is equal to e to the x. And so we know that in this region here, there's going to be something like y, what do we want to call this? We want to call this y naught, right? That's what we're, y naught of x is e to the x. So that part's about as simple as it can come. You can't apply any boundary conditions because there is no differential equation to solve, so you move on. And then here comes one of the things that I neglected to say when we first introduced this concept of a boundary layer. But this will be important to us for this problem. And that is, whenever you encounter a boundary layer, and you know you're going to encounter a boundary layer because our epsilons multiply the highest order term derivatives in our equation, so we know that we're going to have a singular perturbation, which means we know we're going to have an inner solution that we have to match to an outer solution. What you have to do is first rescale your variables and then use the method of dominant balance to find the proper rescaling and then do a regular perturbation. So those are the 3 steps. Rescale arbitrarily, meaning we don't know completely. Method of dominant balance. Find the rescaling. And then perform a regular perturbation on the rescale equation. Regular perturbation on the rescaled equation. And the final step is match to outer solution. To construct a composite solution. Your composite solution implies that you're going back from your rescaled values to x, y, and x. Yep.
Sorry, going back to the outer solution. So is that just an approximation of the outer solution at the order of 1?
Correct.
And I guess what would happen if we try to find the outer solution on order epsilon, for example?
Yeah, so you absolutely can do the same process of substituting y naught. So you can go through the same process here. Let me make some room. So for this approximate region, we can still do the same thing we did before, which is to say, we'll take that y of x is going to be equal to y naught plus epsilon, epsilon y1 of x we can do this, go forward, and that will improve our approximation in this region here. It will still not allow us to apply any boundary conditions. Right. So we'll end up with a new solution y, which will have a correction for the kind of the effect of a small epsilon, which we've introduced into the problem, but it won't allow us to change it to apply any boundary conditions.
Yeah, because y1 prime will fall away, right?
Exactly.
Yeah,
Yep.
okay.
Yep. So we can still do that. I didn't do that here, and I hope that all of you would not do that as well, just for the sake of time, but you can absolutely go back and kind of take the outer solution to a higher order in epsilon. You'll still have the same problem, which the boundary conditions are untouched, but you there's no reason you can't
Yeah,
continue.
that's basically what I was asking.
Yep.
Okay, thank you.
Okay, so this is the general approach here. And one thing I wanted to point out, which I did think I pointed out to everyone in the breakout rooms, but I kind of want to explicitly mention it in lecture. Rescaling in general should take this form. X bar, which is our new X, you can use whatever variable you want for that. X bar should be equal to our old X minus the X location of the boundary layer, so I'll call that X subscript BL, divided by epsilon to the gamma. So what I mean by saying that this is kind of arbitrary is that the first thing we do is we rescale without knowing what gamma is. And then we use the method of dominant balance to find gamma. But this is an important part of it, is that to rescale the equation, what we want to do is move our new boundary condition to the location of the boundary layer and kind of stretch out that boundary layer. That's kind of mathematically, that's conceptually what you're doing with this mathematics, is you're kind of saying, okay, let's move to the boundary layer, let's stretch out that region, and then perform our approximation in this new coordinate system where we kind of focus all of our effort on the boundary layer. And so to do that, you need to tell it where the boundary layer is. Now, the first few problems we worked on, the boundary layer was at 0. So this rescaling just ends up being X over epsilon to the gamma, because X, the boundary layer, was at 0. And that's true here too for the first boundary layer. For the inner solution at y of 0 is equal to 2, our boundary layer location is at 0. So this will look like our prior substitution. I'm going to go a little bit fast for the sake of wanting to cover 2 topics today. So for this inner solution, so I guess we're looking at the red one here. I should have used red, sorry. For this inner solution, what we need to do, I'll make that more, all right, I'll do that here. So for this first boundary layer, nothing really changes, and we get X bar is equal to X over epsilon to the gamma, because X BL equals 0. If we're doing the boundary layer at X is equal to 0, then there's pretty clearly only one relevant boundary condition, which is we need to concern ourselves with the boundary condition, which is Y, and I'm going to call this, I'll go with the original boundary layer at first, original boundary condition at first. Y at 0 is equal to 2. Okay, so there was another point I wanted to make here in the method of dominant balance, which is I want you to feel comfortable approximating complicated things. And that doesn't just mean the complicated thing being this differential equation. It means let's grab this. And part of doing a method of dominant balance is to rescale this thing such that we end up with, let's see here. Oops, that's supposed to be red. So once we insert our rescaling in here, we end up with, what's it look like? Looks like epsilon to the 2 minus 2 gamma times y bar double prime plus epsilon x bar times y bar prime minus y bar equals negative e to the epsilon gamma x bar. So what I meant by that remark of getting you comfortable approximating things is we need to do a dominant balance here to figure out what value of gamma allows our terms that we don't want to lose, in particular that second derivative with respect to y, to remain dominant as we rescale this problem. And the way to do that is you're kind of grabbing the exponents and saying like, okay, as epsilon goes to 0, is this term large? Is this term large? We know that we want the term multiplying y double prime to be large. And you can look at this and say, I don't really know what to make of that term. I don't know how to conceptually think of that. Maybe you do, and that's fine, but it might help you to know that we are approximating things. And so it's perfectly valid for you to say, well, let me just expand this messy thing in a Taylor series expansion. So I can kind of get some kind of concept for what this term looks like, at least around x is equal to 0, or in this case, x bar. And so our scaling for e to the epsilon to the gamma, x bar, if you do a Taylor series approximation, this becomes something like 1 plus epsilon to the gamma, x bar. And now it becomes a lot easier to see what happens to this term. As epsilon gets small, this term goes to order 1, plus higher order terms. This can help with the dominant balance. And I'm kind of emphasizing this point to let you know that like we're approximating our solution. You should be able to kind of say, all right, I don't know how to deal with this radical. I don't know how to deal with this annoying square root term in the denominator. Like you can go forth and kind of approximate your equation by use of a Taylor series expansion to kind of give you a better conceptual sense of how the terms of your equation are behaving. So you go forward with the method of dominant balance, and what you would find is that gamma could either be 1/2 or 1, and gamma of 1 is the one that leaves our dominant terms in the equation. So we kind of find that gamma equals 1, such that our rescaled equation becomes y bar double prime plus epsilon x bar y bar prime minus y bar equals negative e to the epsilon x bar. And at this point, it should be pretty clear to you that we no longer have an epsilon term multiplying our highest order derivative, and we can therefore go forth with a regular perturbation in the form of, oops, perform the regular perturbation and solve. Now here we can apply one boundary condition. That's the boundary condition at 0 to find what our kind of resulting equation is. Let me show you what happens here. So as you perturb this problem, what you should find is, so this is now a regular perturbation. I'm skipping steps, but that's by design. So now you're going to perform regular perturbation, and what you're going to find is that the general solution to this regular perturbation is something that looks like y naught bar is equal to 1 plus a e to the x bar plus b e to the negative x bar. Applying the one boundary condition that you can apply, which is that y bar at 0 equals 2, helps you write one of these constants in terms of the other constant. So we can write our constant b in terms of constant A. So what that means is that once we apply this boundary condition, we can say that our general solution looks like this: 1 plus A e to the x bar plus 1 minus A e to the negative x bar. Again, I'm skipping a solution here. All I've done is apply that boundary condition and solve for B in terms of A. So now the last step we need to do for this inner boundary condition is to say that the value of y as we leave the boundary layer, as x bar gets larger, the value of y as we leave the boundary layer needs to match the value of y as we enter the boundary layer from our outer solution. We're matching the asymptotic approximation from the outer solution to the asymptotic approximation from the inner solution by saying that the value of y as we leave the boundary layer needs to match the value of y as we enter the boundary layer. Physically, this means we need a new color. So let's get a new color. Oh, I already used purple. Oh no. Oh gosh. We're running out of colors. Yes, brown. So now we need to do our matching. And to do our matching, like I just said with words, what we're requiring is that the limit on y bar naught as x bar gets larger, so what we say is as x bar goes to infinity, has to equal, has to equal the limit of our outer solution as x goes to 0. The values of y as you leave the boundary layer need to match the values of y as you enter the boundary layer. You leave the boundary layer as x bar gets bigger towards infinity, and you enter the boundary layer from the outer solution as x goes to 0. And so we're requiring these limits to match. This allows us to find, this essentially says that the limit of e to the x bar, this limit here goes to infinity, which means that a has to be 0. And we get our not really our composite solution, but we get our inner boundary solution that matches we get our solution that matches the inner boundary layer to the outer boundary layer from the inner boundary layer starting at x is equal to 0. So all of this results in y bar naught of x bar is equal to 1 plus e to the minus x bar.
Can I ask a quick question about what you would do if you took out that singular perturbation to epsilon, to the order epsilon?
Can I repeat the question just to make sure I heard it right? Are you saying what happens if you were to take this perturbation out to order epsilon?
Yeah, because then you'd end up with two constants, like call them, I don't know, A and C or something, based on taking that to order epsilon, and you only have one match. Like you're only matching it at one point. So then you have two constants and only one, I guess, equation.
Well, don't forget that to take it out to the next order, we are going to now know. Okay, so actually, let me make 2 remarks. One is we take this out to the higher order. So as we go to here, let's highlight that in a different color. So you're basically saying, okay, we did the first one. Now let's do this second one here. And so there's 2 things I want to remark here. One is We now know why not. And so we're going to add that to our approximation for why. Sorry, we now know why bar not. We're going to add that to our approximation for y bar. The second is that we don't lose that boundary condition we used. It just changes a little bit. Now remember, let's see if I can pull up.
Okay, 1 equals 2. So are you saying that you would have to do the matching asymptotic solutions prior to taking out order epsilon?
Hold on, that was kind of garbled. I'm sorry, I couldn't hear that. Let me make this one note and then I'll come back to what your last remark there. So if you go back to the regular perturbation approach for an initial value problem, and I'll use my highlighter here. So this was the equation. This was the initial conditions. Here's the system of equations with our guess. So this being our guess. At first order, we said here's the boundary condition. The first derivative of x at 0 has to equal 1. So we applied that to order 1. When we went out to order epsilon, we don't lose that boundary condition, it just changes a little bit. So at order epsilon, what we found was that, well, since this term equals 1, my boundary conditions have also been expanded in terms of y, well, in this case, it was x dot not plus epsilon to the alpha x dot 1 plus epsilon squared, well, epsilon to the beta, beta x dot 2. So we don't lose the boundary condition, it just changes a little bit. So at order epsilon here, this term was 1, so 1 plus something has to equal 1. That means that something has to be 0. So our initial condition here changed from this to this. If we go back to our boundary layer problem, our boundary layer, remember that what we insert here for our governing equation here also gets inserted into our boundary conditions. And so we still have that same boundary condition we can apply. And so we can apply the boundary condition once again, and we have no kind of inconsistency. At each level in epsilon, we can apply that boundary layer to find the unknown constant. It's just that the boundary layer might change a little bit because of what happens at the lower orders. Does that answer your question?
Yeah, I think the part I was missing is you would have to do the matched asymptotic solution to find why not, and then you can go to order epsilon. Because now you have a why not, and then you do the matched asymptotic again. Would you do the matched asymptotic on just y1, or would you do it on the full solution of like you add together why not and plus epsilon y1?
You can basically, maybe this will help. You're basically saying that your composite solution should essentially say y is going to be equal to my outer solution plus my inner solution plus this other inner solution minus the matching conditions. Now your inner solutions and your outer solutions can be taken to whatever order epsilon you feel like kind of turning the crank for. And so if you think of it as my approximate solution y is going to be equal to, I'll write this down. So if we think of this as kind of y equals outer plus inner minus match, and there could be more than one, then this thing can be taken out to whatever, each of these can be taken to whatever order epsilon you desire. And they don't have to be taken to the same order. You can take one out to order epsilon and one out to order 1, and you can still match those solutions. The result will be an approximation that will come closer to the true value of y in the regions that you took the approximation to higher order in epsilon. So for instance, say I just said, this is a problem in which I'm studying kind of flow through two parallel plates. And I know that In the middle, there's going to be some Fazio flow, but near the boundaries, there's going to be kind of two different behaviors that I'm interested in studying. In that type of problem, you might say, I don't really care what's happening in here. And what I really would like to do is have a good approximation for what's happening kind of near the walls. So you might take your inner solutions to order epsilon squared and take this outer solution up to order 1. You can still match those together. The approximation in this region is going to be less accurate than the approximations in these outer regions. So it kind of depends on like what problem you're trying to answer. Are you trying to have a valid approximation over the whole domain, or is there a particular thing that you're interested in? And so the key takeaway is to find why you're basically taking your outer solution, adding as many boundary layers solutions as that you have. Each of these can be taken to whatever order epsilon is relevant for your problem. So based on the magnitude of epsilon and the physics that you're interested in, and then you just need to account for the fact that you need to subtract off your matching condition because often you're kind of double counting terms here. Is that clear? If not, let me know. It's okay. Okay, so there's no challenge with going to higher orders in epsilon. We stayed at order 1 here. Going to higher orders means you have to rethink your boundary conditions a little bit. And you'll kind of need to start at order 1 and then kind of incrementally go further from beyond there. But this is the general approach. Rescale with an unknown choice for a gamma, method of dominant balance to find gamma. Use our guess at the solution to insert into your boundary value problem, which means the equation and the boundary conditions. Perform a regular perturbation, and then match that approximation in your boundary layer to the approximation you have outside your boundary layer. And so we have to do it again. So what does it look like if we do it again? So this is for so now we have to look at the boundary layer at x is equal to 1. So here is the case where this becomes important. So now the location of our boundary layer is 1. And so let's go to our, what do we use? We use orange for this. So let's go with x. I'm going to call this x tilde. This rescaled x is going to be equal to x minus x to the boundary layer over epsilon to the lambda, which equals x minus 1 epsilon to the lambda. Why am I choosing a different letter? We don't want to confuse our rescaling of epsilon and make it seem like it's going to be necessarily the same value as what's happening at the other boundary layer. Spoiler alert, it actually will be, but I'm going to call it lambda for the sake of clarity here. Okay, so if we do this rescaling, now our equation becomes, let's see. Now our equation becomes epsilon to the 2 minus 2 lambda times y tilde double prime plus epsilon to the 1 minus lambda times 1 plus epsilon to the lambda. That's x tilde. This occurs, remember, we have derivatives here. And so we're not just inserting x, we're also doing a change in variable such that, for instance, derivatives of y mean chain rule and so on and so forth for second derivatives. This dominant balance, I'm pretty sure no matter what you do, gives you lambda is equal to 1 as you balance these terms. And so there's really not much to think about. And therefore, our differential equation reduces accordingly. It becomes y tilde double prime plus 1 plus epsilon x and you can see clearly, I think, with this approximation that as epsilon gets small, you end up keeping this term and this term because the 1 multiplies it. So while this goes away, kind of the dependence on kind of the variable coefficient on y prime goes away for x being small. This becomes in a sense, a simpler equation to solve. And again, we're going to do this. This is the same exact approach. We're just going to assume that we get this. And we do a regular, we insert this into the boundary value problem. So for the equation and the boundary conditions, and we do a regular perturbation. Again, for this regular perturbation, there's only one boundary condition that it makes sense for us to imply. However, I want to kind of be clear about this. So the only boundary condition left is the one in real coordinates that says y at 1 equals 1. But in our new coordinates, what we really care about is saying that y tilde at 0 equals 1. Why? Because of how we reshifted and rescaled our x-axis. We're looking at the boundary conditions in our new scaled coordinates, where we've now shifted the origin to x is equal to 1. This has a pretty awful solution. I'll give it to you for the sake of fun here. And this solution looks like this. After you apply the boundary conditions, what we find is that y naught tilde is equal to e, which is e is the like exp plus what should we call this? We'll call this capital C. times e to the x tilde. I'm going to introduce a weird little variable called r plus and r minus, and I'll tell you why in a second. So just kind of write this down, and then I'll talk about what I'm writing in a second. So I skipped a couple steps here, and I introduced a new variable. So this is really annoying, and I apologize. Okay, first things first is you notice that the only thing that appears here is the one constant, capital C. That's, in reality, I have a second order differential equation. I should have two constants of integration, C and D, but I applied our boundary condition to rewrite one of the constants in terms of the other. So after I had solved this differential equation, I should have two constants, C and D. I apply a boundary condition, and I determine D in terms of C, which is why you kind of see, which is why it appears in multiplying both terms. The second thing I did is to save awful notation is I introduced this kind of space saving term here, which is just to say that r plus or minus equals -1 plus or minus the square root of 5 over 2. So r plus would be plus here, and r minus would be minus here. That's just to kind of make this thing look a little cleaner. Okay, cool. So this is our approximate solution, and again, the same exact idea applies. This is really quite repetitive, but the idea still applies. The value of y, real y, our actual y that we care about, as it leaves the outer solution, has to be equal to the value of y as we enter the boundary layer solution. And so once again, we have to match these limits. So we'll go kind of go back, and we'll say, okay, I have this unknown constant, capital C, which has to be determined through the matching condition. What is our matching condition? Well, as the value of y as we leave the boundary layer, so the boundary layer in this case is now the y tilde term. Leaving the boundary layer means going towards negative infinity. Think about this for a second. I think this is probably something that you might not jump out immediately. We have rescaled our x-axis. So the x tilde is centered around 0. And what we want to say is that we're starting at x tilde at 0, and we know we have to move left. Because we know we have to move, we're here, and we know we have to move left. And I've said now this is now 0, and if I have to go from 0 to the left, that means going towards negative infinity. I'm pausing for effect because I think this trips people up, or has in the past. The other one is more straightforward, which is saying that if you're in the outer condition and you're, say, here, you really need to head towards regular x, no markings, goes to 1. Okay, so our two conditions are that we have to take the limit as we leave the boundary layer as x tilde goes to negative infinity, and that has to be equal to the limit on y naught. No, this is the boundary layer as x goes to 1. Okay, so what happens? Well, if I take the limit on e to the r minus x tilde as x tilde goes to negative infinity, I get infinity. That's not great. And if I take the limit on e to the r plus of x tilde as x tilde goes to negative infinity, the limit on this one is 0. So let me just try to visualize this for you. So this term I'll highlight in yellow. So remember in your head that this term I'm highlighting in yellow goes to infinity. And this term I'm highlighting in pink goes to 0. So as we come up here, what this is saying is what's what? This is my pink term. That's probably impossible to read now. You're welcome. And this term is the one that's going to infinity. We don't want a term going to infinity. A term blowing up and going to infinity is going to make it really hard to match with a finite value of y. And so if this term is going to infinity, as we take this limit, then the term that multiplies it has to go away. So how do I do that? So this term has to go away to annihilate this term that's going to go to infinity. So that means 1 minus e minus c has to equal 0. Otherwise, you have a term that's going to blow up to infinity, and we don't want a term that's going to blow up to infinity because that's going to make it impossible for us to match this very clearly finite value of y over here. Oh, come on. Or occurring over here. So this is something that I don't think is probably straightforward, but hopefully it makes more sense now. But as a result of this, we find that c is equal to e minus 1. And so therefore, c is equal to e minus 1. Then y tilde of x tilde is equal to e plus 1 minus e times e to the r plus x tilde, where this term is now c. I might have said that with the negative sign before, but I think it was negative c equals e minus 1, so it all flips. So now we have our solution to order 1 in each of the 3 regimes. I'm not sure if what I'm about to show you is going to be helpful or confusing. So, yeah, hold on one second. Question first, yeah?
So I understand the logic for why you wanted to set the limit to negative infinity. And I understand why the limit for the outer solution is to either 1 for this boundary layer or 0 for the other boundary layer. But doesn't the logic that you used for setting the x tilde or x bar going to respectively negative infinity and infinity, couldn't you also apply that same logic to x for the outer solution and set those? Why wouldn't setting x for the outer solutions limits as either infinity or negative infinity, depending on what direction you're going, be the same as setting it to 1 or 0? I stated that unnecessarily confusing. Why can't we set the outer solutions limits as x to infinity in this case?
Oh, okay. Why set the limit?
X to 1 as opposed to x to infinity. Is that the same thing?
Yeah, I don't know. That's a good question. So the question is I think it's here. So So the question is, why are we setting the limit on y to x is equal to 1, and up here we set the limit on y to x is equal to 0, as opposed to negative infinity and positive infinity? And I don't know the answer. I've never thought about that before. I think here's my guess. So we should kind of check me on this, and I don't exactly know where to check, but I'll do my best to figure it out. My guess is that what we want to ensure happens is for x, and I mean x like the original x. I think we are trying to verify that our solution is matched within the domains of x. And we set the domain of x from 0 to 1. And so I think what we're really trying to do, part of the reason why you would pick the limits as you go to 0 or limits as you go to 1 is you're basically saying, and this boundary value problem should only be valid on this domain. And so we want to make sure that as x goes to 0 and as x goes to 1, we kind of set these conditions. So that is my guess. And
It's also consistent with saying, just intuitively, if you're from the perspective of boundary layers, when you're looking at the boundary layers, whatever dynamics you're seeing there, you could extend to whatever infinity. But whereas you're looking at the other solution, you know that it's bounded to somewhere.
yes, I think that's fair to say. So just to repeat what was said is kind of, in that rescaled coordinate, you're basically just trying to get yourself out of the boundary layer. But in the outer solution, you're really trying to get to the limits of the domain. It's a good question, and I hadn't thought about it before. So that's a good one. Okay, let me first show you mathematically what's happening, and then I will probably confuse you, but try not to confuse you. Okay, so this is good. So let me just remind you what we have here. I don't even think I ever wrote this down. So let's write it down up here. So we have 3 solutions. Outer solution, inner solution near the origin, inner solution near x is equal to 1. So the matching looks like this. Mathematically, the composite solution looks like y should equal y naught of x plus y bar of x bar plus y tilde of x tilde outer plus inner, and then we have to subtract off the matching conditions. The matching conditions were the condition on y naught at 0 and the conditions on y naught at 1. Where do these come from? These come from here. Y naught at 1, y naught at 0. You could just as easily have chosen to do y bar naught at infinity and y tilde naught at negative infinity. We've already set these things to be equal to each other, so it's perfectly valid for you to use either of them. This is equal to 1 plus e. I'm not sure if it's useful for you to visualize this, but let me try it anyway. So maybe this is helpful. So mathematically, you can kind of, if you're good right now, you can kind of turn off your brain and not let me confuse you. But so mathematically, what I want you to do is to say, add the inner solutions to the outer solution, subtract the matching condition. conceptually, if you're having trouble understanding why you're subtracting the matching solution, let me draw a diagram for you. Here's my diagram. Here's my domain, real X, and we know that the width of this boundary layer is of order epsilon. That has to do with the fact that our scaling was for 1 over epsilon. So that means the width of the boundary layer is going to be epsilon. That happened in both boundary layers. And for both, what we can do is we can say, if we're adding these solutions together, we really need to think about what the values of these terms are in each of these domains. So for instance, we know, first and foremost, that in the outer solution, y is equal to y naught. And that's what we want to keep. In the inner solution near x is equal to 1, we know that y should be equal to y tilde. And in the inner solution at x is equal to 0, we know that y should equal y bar. I should probably box these, shouldn't I, to be consistent. So that's this, and that's this. However, we also have to be aware that there's also a solution for y here. So why not, or y, I guess, is equal to, let me write this down and I'll show you what I'm doing. Okay. Oops. Do that red. Okay. So the red are the y bars, the blue are the y's, and the orange are the y tildes. What I'm trying to show you here, and I'll try to do this clearly. So let's take the inner solution here in this region. We know that in this region, the thing I boxed is the approximate value. And what we're doing when we add these terms together is we're actually adding them over the entire domain. So if I add y naught, I'm taking y from x is equal to 0 to x is equal to 1. And so you might be confused as to where this 1 and this e comes from, and let me show you that. But basically what that means is as I add these three equations together, at each layer, I'm kind of adding a 1 plus epsilon, 1 plus epsilon, 1 plus epsilon. So let's look at this one here. Y naught. So y naught of x, we know from our approximation, is equal to e to the x. So we can look at what that means at the boundary layer. So I'm looking in this limit over here. And y naught at x is equal to 1 equals e to the 1, which equals e. So by adding the outer solution to the inner solution over here, I'm adding an extra t. If I do the same for y bar, I would say that y bar of x bar is equal to 1 plus e to the minus x bar. If you don't remember that, you can just scroll here. That's all I'm doing. And therefore, if I look at this for y not bar at 1, I get 1 plus e to the -1 over epsilon, once I substitute in back for real x, and this term goes to 0 as epsilon gets smaller. And so this leads to y not bar is equal to 1 at this level, and y not is equal to e at this level, so 1 and e. So at every, we could keep going. We could do this for here and here and here and here. And what we would see, this is not something you have to do. This is more just a way of visualizing what we're doing here. When we add these three solutions, what we're doing is adding a 1 plus epsilon, 1 plus epsilon, and a 1 plus epsilon at each layer. And so what you need to do is you need to subtract off 1 plus epsilon. And so that's the kind of conceptual way to think about these matched asymptotics, is when you add these approximate solutions together, you have to take away kind of what's happening in the other solutions across that domain. Okay, zoom back in. If that was too confusing, or if I totally explained it poorly, then you can kind of click back in mentally. And this approach, add up the inner solutions and the outer solutions to get the composite solution, will yield your final approximation for y, which is y should go as e to the x plus e to the negative x over epsilon plus 1 minus e times e to the r plus x minus 1 over epsilon. And if you were to come back and plot this, what you would find is that it does pretty well. I think I will put the notebook, Mathematica notebook, where I plot these results online. I think this is one where I just kind of used Mathematica lightly. So I'm just kind of plotting the results. But what you find is that you end up with a curve, believe it or not, that looks a lot like this curve.
Why don't you subtract the matching condition twice? Or for one for each time, one for each inner solution?
It's mostly, so the question was, why don't you subtract 1 plus epsilon, which is a matching condition, twice, kind of one for each condition. And it's more so that what is happening is the matching condition is kind of, the first matching condition basically adds a 1 plus epsilon in the boundary layer range, in like the near the origin. The second one adds it near the other boundary layer. So the result is adding the three solutions together leads there to being a 1 plus e across the entire X domain. So instead of it being like you're adding 1 plus e multiple times, think of it as you're adding 1 plus e over portions of the domain. And when you get the whole solution, you've then added 1 plus e over the entire domain. And so you subtract off that 1 plus e.
So your matching condition is averaged over the domain.
The matching,
Yeah.
The matching condition, what happens as you add it is that you now have this extra term that appears over the entire domain that you're not subtracting off of it. So it's not that you add it multiple times, it's that to match over the entire domain, you've added that term to the entire domain. That's a good question. It's confusing for sure. That's what I was trying to get with this diagram down here, but it probably made things worse. Questions? I recognize that there are kind of various things that are tricky about this. However, I want you to get to the point where you can kind of think through it in this way here, where it is, we start with an outer solution, which we have to do a regular perturbation. We address the inner solution by rescaling with gamma, using the dominant balance to find the proper rescaling. So what is gamma? Now you have a problem that can be done using a regular perturbation over your rescaled equation. And then you match it to your outer solution to create your composite solution. And that's your kind of matched asymptotic expansion over the kind of entire domain of the boundary value problem you're studying. So while there's lots of intricacies along the way, there's a procedure. You can, I kind of use that joke of like turning the crank and kind of powering through, but that's basically what you're doing is you're kind of going here, you're saying, okay, let me do a change of variables. Let me use the method of dominant balance to figure out what gamma is. Let me put that in. Oh, now I assume a solution that looks like a regular perturbation. Do a regular perturbation, solve, apply the boundary conditions, match, and go on and keep going. And I hope that you're comfortable with this enough that you can do this on your homework now and get some practice with it. And part of the goal for the breakout rooms was to give you some practice, but I wanted to kind of make sure that we all got there so that now you can kind of go forth and do these things on your own. What questions do you have? How about this? How about take like a few minutes? We'll come back at 12:15 or 12:16 or something and come back with questions, and then we'll move on to, I just want to show you one other thing that can crop up. We won't be able to have time to go through it completely, but I think it's worth seeing. So let's take a break.
Professor Holmes,
Yep.
can you hover over the limits for the second boundary layer? Okay, thank you. Oh, I don't have a question on it. I just need to
That's
look
okay.
at it again. Thank you.
You have office hours after this class, right?
Correct. I do have, yes, I have office hours after a class.
Professor Holmes,
Yep.
can I ask a quick homework question?
Yes. Although I might not have any idea what the answer is.
So it's just for problem 1B. I've been getting tripped up on this. because at first glance, so it's the one where it's like epsilon x cubed minus x minus 1 equals 0, and it's just that equation. So it looks like pretty similar to the first like intro problem that we had to singular perturbations, where it was like epsilon x squared plus whatever equals 0.
Yep.
So then so with that first intro problem, it was like as epsilon goes to 0, then you have a singular solution rather than 2, right? But with this, so like this one looks similar, but then as you like analyze it a little bit, like as you plot epsilon x cubed and then x plus 1, you notice that you have one solution for larger epsilons, and then as epsilon goes towards 0, there's one point where you have 2 solutions, and then you get to 3 solutions as epsilon goes to 0. And so let's see. So I think like with the regular perturbation, I got something that sort of looks like one of the outer solutions, although it's not really a boundary value problem. And then like when I tried to do the singular perturbation, it just doesn't really make sense. I don't know if I'm just approaching this wrong. I need to like take a step back, but if you have any hints.
I guess one of the things I would say, and this could be part of the challenge, is that this is a third order polynomial and you always have 3 solutions. The thing that I think trips people up is that for I think third order, this is like the Euler number, which you may or probably don't remember. I barely did, which basically tells you like the characteristics of the solutions. So, for a second order polynomial, you basically like how many real solutions do you expect and how many imaginary solutions should you expect? And so for this one, I believe the answer is you expect 1 real and 2 imaginary for a third order polynomial. And so you're always going to have 3 solutions. It's just that they might be switching between how many of them are real or in what region are they real or imaginary. I don't know why the regular approach wouldn't work for rescaling this. It might be the rescaling requires, it might be that the regular perturbation, you can't assume integer powers of your power series, but I can't remember. I haven't done this one in like since the last time I taught it. So it's been like a year. So we can chat maybe on office hours or something. I can see what you're up to, but I guess the point I would make is the number of solutions is dictated by the order of the polynomial, but in what regime do you have a certain number of those solutions being real or imaginary could be maybe tripping you up. So maybe we can chat. Pretty clearly as epsilon is exactly 0, you have 1 real solution, and that is that x is equal to 1. And so the challenge basically is rescaling to find those the roots for the small epsilon. So I don't have a good answer for you right now because I'm not exactly sure what maybe went wrong. So maybe we can chat in office hours.
Okay, I'll hop onto office hours after class then.
All right. What questions popped up during the little break there? Yeah, everyone in here?
So one thing I was just thinking about in terms of good approximation. So is it a requirement that if we do our outer and inner solutions on the same order of epsilon? Or for example, could you have the outer solution on the order of 1 and then take the inner solution to the order of epsilon and then match them still?
No, you can still match them. Now you're going to be matching them at maybe a value that has some inherent error to it because you
Sure, yeah.
But that's going to be true at no matter what order you take them to. But they can be done to different orders.
Yeah, because I would assume that
I don't know why you necessarily would. I guess there's some that might be harder to do at some orders than others, but yeah, you can.
Okay. Yeah, because I would think for different regimes, sometimes an order of 1 would be perfectly fine, whereas other.
That's exactly the case.
Yeah. So
Yeah, that's often true, and especially if what you're interested in is occurring in a particular region.
Yeah,
You know,
okay, cool.
Other questions? Ah, what happened? Went to sleep. Okay. All right, I'm back. So what we've realized, what we've learned is that when we find an inner solution or when we find an outer solution, what we've found is a solution that is not uniformly valid over the entire domain. Then we do a little bit of extra work. We construct a composite solution that is uniformly valid over the whole domain. Okay, so we found an example of kind of a lack of uniformity that can occur. That lack of uniformity can occur when you have singular perturbation problems, but that lack of uniformity of your approximate solution can also occur in other problems, in particular, solutions that change over time. And so what I would like to show you, and we're not gonna have time to go through this carefully, so this is gonna be more for you to be, I would say this is about awareness. Rather than it is being able to, demonstrate this on your homework assignment. And the problem I want to give you is kind of is probably perhaps the most classical problem in mechanics, which is that of the swinging pendulum. And so the pendulum problem, as you've all seen before, here is vertical, here's my pendulum. And this is the angle of that pendulum as a function of time. And coming from force equals mass times acceleration, and the forcing coming from gravity, you can derive this governing equation to find that the governing equation for the dynamics of this is, I guess that should be double dot, right? Well, I'll just keep it as written so I don't make a mistake. Sine theta equals 0. It initially starts at rest, so the initial velocity at time 0 equals 0. However, in order for this pendulum to swing back and forth, it can't start at 0, otherwise it'll stay there forever. And so what we do is we say that at time is equal to 0, the initial angle is some small value, epsilon. So this comes from the rescaling here of this problem. And so we start at rest, where we start with some small initial inclination. We push the pendulum some amount epsilon and we let go. And we let this thing oscillate back and forth in the absence of any damping, in the absence of any friction, so this thing will go forever. Not physically realistic, but some things in, with limited friction and engineered properly can swing for a very, very long time. And that's the key point that we're going to talk about today. We know in the absence of damping, this thing will swing back and forth forever. So we kind of can guess the solution is going to be just like this kind of sinusoidal swaying back and forth. Clearly, the thing that's different here is epsilon doesn't multiply the highest order term in the differential equation. In fact, epsilon only enters the system of equations that make up this initial value problem in the initial conditions. So epsilon appears in the initial conditions. So what do? Well, the first thing is that it doesn't change our general approach. We still begin by expanding for our solution as we normally would. We still say, well, I'm going to assume that theta is going to equal theta naught plus epsilon for the alpha, theta 1, so on and so forth. One of the challenges here is that in order to satisfy our initial conditions, we find that this thing has to equal 0. So we don't actually have an order 1 solution here. And so what we find is that if this thing goes away, then our approximate solution looks a little different. And it looks something like this, that if that goes to 0, we can pull out an epsilon. Oh, we also find, sorry, that alpha is equal to 1. What we find is that, so we really write our scaling like this. This allows us to get our initial conditions to be matched. Does everyone see this? Like rescaling this thing is kind of silly because if we choose this top rescaling here, theta not has to be 0, otherwise we don't get epsilon occurring when time is equal to 0 for theta. We know that the initial condition stipulates that at time is equal to 0, the initial angle has to be 0. So what do? You have this nonlinear term. What's the nonlinear term? The nonlinear term is this sine theta. And again, whenever you're approximating something and you have a messy nonlinear term, approximate the nonlinear term. Taylor series expansion of sine of theta yields theta minus 1/6 theta cubed, and then so on and so forth. Only odd integers will remain due to the symmetry of that periodic function sign. And I'm just going to skip some steps here for the sake of time to say that we've already said there's no order 1 solution, so there's only going to be at lowest order an order epsilon solution. And so at order epsilon, what you would find is that our solution becomes fairly straightforward. Second order ODE for theta naught. Theta naught at 0 equals 1. And theta naught prime at 0 equals 0. And the result of this, so you need to have an equation in which, if you don't remember, this equation in words says that, this equation in words says that give me theta, that when I take 2 derivatives of it, I get theta back. So that means you're going to have a sine or a cosine. And then the fact that this initial condition sets it at 1 at time is equal to 0, that tells you that you're going to have a solution that's like cosine. And so that means our solution is theta naught is approximately equal to cosine t. And then we put that back into our approximate solution to find that theta is going to be equal to epsilon cosine t. Okay. Here's the problem. So let me show you the problem. I'm going to switch screens really quickly. So this is a initial value problem. We can solve it numerically. It's a pendulum swinging back and forth, so we expect this periodic motion. Everything looks fine. And look, we have a solution that says we can approximate this answer as theta, which is what the y-axis is here, should go as epsilon times the cosine of t. Okay, so we do that. our approximate solution, cosine of t. I'm actually going to now non-dimensionalize theta by epsilon, so I'm going to plot theta divided by epsilon as a function is equal to cosine of t instead of theta is equal to epsilon cosine t. So I'm applying theta divided by epsilon here as a function of time, and here I'm going to plot theta divided by epsilon. And look what happens. You get a very different type of problem appearing. It almost looks like you should have like 3D goggles on. What's the problem? The problem is in this kind of time-dependent problem in which there's no domain for the time just kind of can go on indefinitely. What you find is that the approximation that you used works really well for short times, and then over a long period of time starts to drift away from the actual solution. The actual solution is in red and our approximation is in blue. So unlike before where we kind of would like have an approximation that maybe didn't accurately predict the value, this one's actually kind of doing a poor job at predicting the period. So the period of our solution at order 1 in our, or sorry, at order epsilon for our approximation doesn't capture the period that we would expect from numerically solving this equation. So this is different. This is different than what we've seen so far. And your first thought would be, well, I can fix this problem without any challenge. All I need to do is take this out to order epsilon cubed. Why is it not order epsilon squared? Well, this is, as we've said, has a symmetric problem to it. So if you did order epsilon squared, it would drop out. You're only going to have odd numbers for your epsilons. So I'm going to skip some steps again. I just want to show you what's happening here. Oh, question somewhere.
Screen.
Screen. Let's see. Oh, I haven't switched screens. That's what you're saying. Haha. So I'm going to switch back to writing. And we'll come back to Mathematica in a second. I'll post this code as well if we can play with it, because I'm skipping a lot of steps here. Okay. You don't see this. Why don't you see this? There we go. Okay, cool. So at order epsilon cubed, what you end up with is a different differential equation for theta 1. It's going to be theta 1 double prime plus theta 1 is equal to 1/6 theta naught cubed. We know what theta naught is. Theta naught is that cosine of t term multiplied by epsilon. Our boundary conditions become theta 1 at 0 equals 0, and then theta 1 prime at 0 equals 0. Again, I will point out to you that this this initial condition changed from this one. For the same reason it's changed every time, we've already satisfied that initial condition, so the initial condition at the higher order has to be equal to 0. You solve this equation, you get something quite messy, but I'll write it down anyway, and you end up with something that's like theta 1 is equal to 1/16 times t times the sine of t. Whoa, it's a mess. Let's see here, plus 1 over 192 cosine of t minus 1 over 192 cosine of 3t. Great, we have a solution. We plug this back in to the details of this aren't important. So if you're like scrambling to write this down fast, I'm going to upload my notes. The important thing here is actually what's going to happen as we do this. So don't worry about the details of solving this. If you want, you can work through this on your own. But what I want to get to is kind of what happens. And so we solved this to order epsilon. It worked, but it didn't capture the period that well. Maybe taking out the higher orders in epsilon will help resolve that period problem. So we now have a theta 1. We go back here, and we have our theta naught solution. We have our theta 1 solution. we plot this solution. Steal the screen again. So we take this out to order epsilon cubed, we plot the solution, and what we find is, well, we actually didn't fix anything. We might have even made things worse. So you'll notice that first things first, I think we capture the period over a longer time. So maybe out to, say, 75 seconds as opposed to out to like 25 seconds above where the period is captured. But clearly things start to go crazy over here. And we have this term in which the amplitude of our pendulum is increasing. So it's almost like saying I push the pendulum a little bit and it starts swinging back and forth and then swinging crazier and crazier back and forth. So what is happening? What have we done wrong? The answer is that in our approximation, due to the nature of this having kind of sines and cosines here, that's one part of it, in which the derivative of that term kind of pulls out at time. So you end up with that t sine of t. So as time increases, you have this term that is kind of growing in magnitude. Due to the fact that we have this kind of periodic motion and the fact that this periodic motion is unbounded and can go on forever, we end up with the appearance of what's referred to as a secular term. And our goal to get a uniform approximation in this case is to eliminate that secular term from appearing. So we have to eliminate the term that is causing the amplitude of this thing to grow over time. We're not going to go through the whole process of how you do this, but I am going to show you the basic idea, because once you have the basic idea, you should be able to kind of go through this process. Everything else kind of remains the same. There's basically two steps when you have something like this. So if you have a problem which is unbounded in time, and you're trying to approximate a solution, you have to be aware of the appearance of secular terms. And those secular terms will cause your approximate solution to get worse and worse over time. Okay, so what's happening? The first thing that's happening is that we recall, there we go. The first thing that's happening is that, think back to that first cosine graph. What's happening is that we have some fast dynamics, so this thing is swinging back and forth. And then we have some slow dynamics, which is that the period is changing over time. If the period wasn't changing over time, then our cosine t approximation would work great. But clearly the period is changing slowly. So there's some motion back and forth, but that period is kind of slowly evolving. So the way you address this is in two parts. First step is you introduce two time scales. This is why it's referred to as two timing. Something is changing slowly over time. There's one basic period of motion, one basic period of oscillation, and then one slow scale in which the phase is changing. So we introduce two time scales. The first is that basic period of oscillation, so we'll call it T1, and that's just going to be like T. And the second is accounting for the fact that slowly things are changing over time. So we end up with T2 being epsilon to the gamma times T. We don't know gamma, just like before. We're going to let the problem figure this out for us. We have to go through the whole process as we've done before, which means inserting these things into our problem, just like we did for when we have a boundary layer. When we have a boundary layer, what we do is we rescale the equation such that we can kind of focus in on the boundary layer location. For this problem of multiple time scales, what you end up doing is doing a change of variable to kind of separate the axes into two different regions. We're not going to go through the process of doing that here, but step one is a change of variable. And step two is elimination of the secular term that appears. And so the end result, I'm just going to show you what happens at the end result of this is what you end up finding is that the end result is that our actual solution for theta is such that it has epsilon multiplying the cosine of time minus something that is slowly evolving the period. Oops. And you can kind of see it mathematically. At order, when time is small, this basically behaves like cosine of t. But as time grows, this small term increases in magnitude and accounts for the fact that this period is actually shifting. You can do all of this. I'm not going to go through the details of it. You have all the machinery and the capabilities to solve this problem. It's the same as before. We have a change of variable. We need to do the chain rule, reformulate the differential equation with this new scaled variables. We need to do our regular perturbations and now we're going to have kind of the challenge with this problem is we take a problem that is an ordinary differential equation and we complicate it by turning it into a partial differential equation. How do we know that we just changed it into a partial differential equation? Well, now we're saying that we have to consider derivatives of theta with respect to t1 and t2. It turns out that the process of working through this problem is not as bad as it sounds. There are some things you probably learned a while back in differential equations that would give you the tools to map this PDE onto a simpler ODE. I'm not going to worry about that for right now. I mostly want you to know that when you're dealing with approximating solutions, there are kind of two cases in which your approximate solution will not approximate the behavior over the entire domain. The first case is when you have the appearance of a boundary layer. And then you're going to need to have a solution that approximates it in the boundary layer and outside of it. And then you need to kind of match those to get a solution that approximates over the entire domain. The second case is in a dynamical problem that is unbounded in time. What you can have is that your solution can slowly change over time. And in that case, instead of having a boundary layer, what you end up doing is kind of separation of time scales, looking at what's happening in kind of short times, looking at what's happening in long times, and having to construct an approximate solution that accounts for this kind of slowly evolving dynamics. I think, let me just check really quickly. Yeah. Okay, I'll just show you. This is probably not that exciting, but one last thing I'll show you, and then I'll leave this, take questions. So if you account for this secular term, then you can capture these dynamics over an extremely long time scale. And of course, as you would expect, you might need to consider epsilon to the fifth terms if you're taking this time to say order 1,000 seconds. And this will also start to drift eventually as well. But it's a bit messy, but this is kind of another example of how things can get complicated or lead to a non-uniform solution in the approximation using perturbation methods. Yeah, question?
So this is something to be aware of or I guess more general way to state it would be this is something to be aware of when one of your independent variables or domain is unbounded in one direction.
Yes.
What if it's just completely unbounded? Then you're just approximating around the region you're interested in, right?
Yeah, if it's completely unbounded, I mean, you know, what does that, I guess, mean, I would say? Because if you have an initial value problem, you're typically starting at some location. Now, maybe you're starting just with some descriptions of like initial speeds or speeds at 2 points and letting it kind of go where it will go. I'm not.
So to add on to that, I guess does that mean something like a, you know, problem where you're modeling like impulse response, you know, waves or acoustics?
Yeah, I think that's a good example. If you kind of have an impulse response in like an infinite medium,
Yeah.
and that wave is going to propagate, then yes, that would be a good example as to when you.
Or even in a bounded medium, because in terms of time, you're still.
Yeah, in terms of time, you can let this thing kind of ricochet back and forth. Even if you're, yeah, exactly. If you're spatially bounded, you kind of hit it, and it's just kind of have a wave that's propagating back and forth, and there's nothing to dissipate that. Then exactly, that would be another.
Would this still have been valid if we included attenuation or dispersion or those other?
I think attenuation or dispersion kind of has the effect of making the problem no longer unbounded. Because now there's a characteristic time scale where if everything kind of disperses over that time scale, then it's not going to kind of evolve infinitely in time. And so you kind of, it's like a more physical way to stop this, I guess.
So in that case, we would be sort of imposing a boundary condition where everything's at rest at some end.
That's kind of physically what it means, I think, when you're saying that like, there's something that is going to dissipate that energy. It means that there's a time scale in which that energy will be dissipated. And so then it kind of imposes like a bound on the time of how long this could go. But it's a good question. So again, I went through this really fast. The purpose of this was mainly for you to be aware of this problem, especially if you're doing something in dynamical systems. This is something to be aware of and understanding kind of the general procedure of, even if we can go through the details. All right, I'm over time. Thanks everyone. I'm gonna jump on office hours in a few, and hopefully you all come with awesome homework assignment solutions on Thursday to show your classmates. Thanks everyone. Have a good one.
Bye, Professor.